don't just freely use it. Let me know if you need something specific or whatever, we can work through it. So, you know, lawyers. So then here is my team. So I am second from the left there. Tom Taylor's on the very left. He is our resident PhD chemist. He has many years in the roofing and material manufacturing industries. I'll skip me for the moment. Jennifer Keegan and Ben Meyer, they are both also architects. I am also an architect. So we have this nice team of architects and a PhD, you know, chemist doing building and roofing science, which is really great. Jen, Ben, and my backgrounds have a lot of similarities. We've both been in the what I call the forensic investigation side of things. This building has a problem. Please come out, find out what the problem is, write a spec, do some QA, make sure it gets built correctly the second time around or the whatever time around. So that has formed a lot of what we have learned over the years. Ben's been in the actual real estate market for a while. So there's a lot of mixed background and a little bit more about me. I did that forensic engineering thing right out of college. I actually have a master's in architecture structures option. So if you want to talk about wind loads, I love talking about wind loads. I get that concept. And then I spent a bunch of years in the trade association business. A lot of time at National Roofing Contractors Association. You can learn so much by listening to contractors communicate what works and what doesn't. It was foundational for me. And then I worked for ARMA, the asphalt roofing manufacturers, roof coating manufacturers for a while. And what I told Jason beforehand is I'm coming up on my 4th year at GAF. And I think what's important about that is I was the 3rd employee in the building science department, building science group at GAF. We've been focused on how to, you know, have high performing roofs as a group within GAF for now 5+ years. So GAF really has this commitment to how to make things work correctly, how to design correctly, and on top of, you know, good quality materials and all that kind of stuff. So that's enough about all of that. Let's tell you what we're going to do today. So we're going to talk about airflow and strategies for reducing it, because that's a big factor in energy efficiency. We're going to talk about insulation and fasteners and really what fasteners mean to thermal bridging components of roofs. We're going to look at reflective roofing. I know where I am speaking. We're in Texas and Oklahoma. I'm going to give you some foundational information on reflective roofing and why it matters, and hopefully try to bring at least commentary to your particular region of the world. And if I didn't say earlier, I'm up in the Chicago region, so I get a few more bits of annual seasons than maybe you guys do, but I know there's no loss of snow and cold weather, certainly in Oklahoma and some of the northern parts of Texas. So anyway, and then we're going to talk about sort of putting it all together for an energy efficient roof system. So another way to say this is we're going to talk about roof reflectivity. We're going to talk about fasteners. We're going to talk about insulation and thickness and all of that, what we do with air barriers, how location affects, and we're going to actually get into also energy and energy types and how to do some modeling and what models are out there that you can rely on for some good quality information. So with all that, why does all of this matter? And hopefully this is a review and not necessarily new information. But you know, residential and commercial buildings in the United States use 40% of all energy and 75% of all electricity. So buildings use a ton of energy, and clearly reducing the amount of energy that buildings use, you know, is important. You know, we all win with lower operating costs, reduced carbon dioxide emissions, and you know, quite honestly, if your building occupants are happy, they are going to be better, better renters, leasers, owners, just happier clients, if you will, if you're leasing to folks. So good buildings do actually provide a better working environment. And I think sometimes, we like to show these, and talking about the graphic on the right here, we show these big, tall buildings, and, I'm the roofing guy. So, it's a little bit of a thing that, we talk about a roof on a 10, 20, 30-story building. But I think it's really important to know that the vast majority of roofs are on buildings that are 2 stories or less in this country. So we show the pretty downtown shots because they look good, but the bulk of roofs are not on those types of buildings. They're on low, large buildings. And so what we do with the roofing system has a great effect on energy efficiency overall. So we know buildings use a lot of energy, and we also know that it's declining over time as we get better at all of these things being increasing insulation levels, using reflective roofs, building air tightness, building air tightness into the facade, into the enclosure, obviously using better HVAC equipment. And one of the things that's so hard to control is just what plug load is. Occupants can plug in 47 things. I mean, thinking back to earlier presentations on this similar topic, 20 years ago, how many people had more than one TV? More than, hell, did we have a computer 20 years ago? Now we've got 47 TVs and 13 iPads, and everything's plugged in, and I'm sitting in front of a computer that has 3 monitors. I get these are very low draw types of pieces of equipment, but additive over the US with all of the equipment that we put in buildings, we're using a hell of a lot of energy. So any place we can as the building components, as the building folks, to reduce that energy use is really, really imperative on our part. So good job, code folks, bringing updated codes. I am not about to touch today the ICC's choice of going to IECC as a standard versus as a model code. We can talk about that later, but I'm not gonna really get into that too much. So
you're not going there, huh?
No, I'm not going to go there. And you know what? I will make one comment. Depending on who they put on the committee, it could be really great or it could be a real disaster. And I think,
well, I'm the lone voice in the efficiency world that's not alarmist because of that exactly. And actually, 2 days ago, I had the senior, a lady with ANSI, did an hour and a half all over the standards process.
Yeah.
And depending on how, like you said, depending on how ICC sets that up, it could be better. I mean, if they state objective goals for improving efficiency from addition to addition, I think it's going to be a good thing. Honestly, I really do.
Right. Yeah. I think it does bring a little bit of an enforcement issue. Staying up with changes will be a little bit harder because we don't have that complete volume coming out every 3 years. The active process of updating the code at any point in time is going to be new. It's something we're just going to have to get used to. So, all right, good commentary so far. And again, Jason, cut me off whenever you need to.
You're good.
So let's get into this stuff. Here's our 3 topics for today: dark versus cool, absorptive versus reflective, however you want to talk about that. Thermal bridging and what we can do about it. And that's really a key component, is what we can do about it. And then airflow in roofs, which is a little bit less of a thing in your general geographies, but it's still relevant for a number of reasons. And we'll really talk about that. So, all right. And I will say too, if anybody has questions, go to the Q&A, drop them in there. Jason's going to be looking at that. I'll glance over at him on occasion. So, dark roofs versus reflective roofs. We know this. Dark roofs reflect 5%, 20% of the sun's energy. cool roofs reflect 65, 75, 85% of the sun's energy. And, you know, maybe in San Antonio and in Austin and Dallas and Houston, we recognize this, but the further north we go, which we know is the way the code is written, you know, prescriptively, you can put a white roof in zones, climate zones 1, 2, and 3, barring other trade-offs with energy efficiency for new buildings. One of the things that I should say is in the roofing industry, some 70, 80, 85% of the market annually is re-roofing. We don't put roofs on just new buildings all the time, and of course that cycles to some extent with the market of what is being built versus what is being re-roofed. So a lot of the things that where we come from in the roofing industry are based on the premise that we are doing this re-roofing project, so we tend to look towards the prescriptive path because we're not doing whole building energy modeling from that perspective. So, you know, continuous insulation table, prescriptive path, we look for insulation. Reflectivity, we look towards, you know, prescriptive path from that perspective. So I think that just helps sort of set the table on where I'm coming from and why I don't really ever talk about whole building energy modeling and trade-offs. So, but the argument in the roofing industry, of course, is that cool roofs save energy. We do truly believe that. But there's always been this discussion about, do dark roofs actually provide a heating benefit in the wintertime? And again, may not be entirely relevant where you folks are, but I think putting this background out there for all of you, I think really does help this discussion overall with all of this. So just recently, we noticed an article, and some of this information is a little bit old, but it was just nicely packaged in, Interface magazine. And that's where this graphic actually comes from. And I like it because this is so basic about reflectivity, but this is so much more detailed about what really happens when that sunlight gets reflected and what percentage heats up the atmosphere, what percentage heats up the city, what's truly reflected, and how much actually heats up the building. So, you know, breaking this down also debunks the idea that, you know, reflecting energy off of a white roof actually increases the heat in the atmosphere. And according to Lawrence Berkeley Labs, we are heating the atmosphere nearly 4 times as much with a black roof as we are with a white roof. So just more information, more data to chew on.
That is a super cool graphic.
It's a super cool graphic. Yeah, exactly. So, you know, much more reflected. You know, what actually surprised me most about this was that only 4.5% of the sun's energy actually heats the building. You know, we've reduced that by 3-fold, and we're down to 1.5%. I would assume that 4.5 would have been much higher. So
absolutely.
Yeah. So this is good, a nice way to frame this entire discussion. So putting some real numbers behind this, you can take your infrared gun, go up on the roof and lay out different materials. These temperatures were taken on a day when it was 89 degrees out. EPDM, our black rubber roof membrane, has sort of been the standard that we judge from, if you will, because it has the least amount of reflectivity and gets the warmest. And you can see, you know, upwards of 173 degrees. We put just a little bit of light gravel on it. That's not even that light. And we bring the temperature down, you know, 12, 15 degrees. That BUR cap sheet's still a little bit damn hot, you know. And then our reflective single-ply here, even though, you know, it's still really warm. It's, you know, it's 40+ degrees cooler than that black EPDM. And, you know, we've all driven down the road and seen the radiation coming off of the asphalt when we're driving. And, you know, you get that up on an EPDM, and I've had people say you got to wear thicker soled shoes because your sole burns a little bit when you're on an EPDM roof. The contrary is a reflective single-ply means you might, you know, screw up your eyeballs because you need such heavy duty sunglasses. But, you know, there's trade-offs for all of this stuff, and we actually will get into some of that. So just some perspective on how warm roofs really get. Then let's see here. So, you know, we could look at this very simply, but we really need to dive into some of these specifics, like cooling costs when we're talking about electricity use for cooling are 4 times higher than what we use for gas heating. And you know, we'll get into the sources of energy here pretty quickly. And I know that it varies across the country. And what I will say, anything that we talk about today is generalized modeling for the most part. And I'll say it more than once, for specific locations, for specific projects, it really makes sense to do your own modeling and figure out what parameters are influencing energy efficiency for that particular building. And that's, I suppose, a bit of a conversation towards an architect or an engineer who's designing a building, architect, designer. But, you know, we also know that white's been used for a long time. We know we wear white t-shirts when it's summer out, and, you know, you can wear your black t-shirt at night when the sun's not hitting you. But, you know, it makes some sense, and we can put some practical application behind some of this too. So what other things are we really needing to think about here? So, you know, how much insulation makes this whole discussion of color not valid or ineffectual, I guess? You know, does electric heat actually mean something where we, you know, want to reduce electric heat when we have the sun hitting a warm roof or a roof in the wintertime so that we actually gain more energy? You can see from that prior graphic that we aren't gaining a ton, but we'll get into that a little bit. You know, some people just don't want to look at bright white roofs, which I really kind of commented on. So here's a thought. We always have this conversation that we're talking about dark absorptive roofs or white highly reflective roofs. How about some middle ground? How about a grayish TPO? How about a dark gray? How about a light beige? How about a medium beige? You know, most manufacturers of TPO and for sure are white, beige, gray. You know, we can make this work with you know, these ideas. It doesn't, not to be cute, it is not just a black and white discussion. So things for us all to think about here.
And the gray and beige don't have trouble meeting the solar reflectivity or the.
It depends on where
climate zone,
depending on what the actual values are, what the local requirements are. So to your point, in your area, prescriptive path, re-roofing, you're going to use a white roof.
Yeah.
Almost exclusively. When you are doing an energy modeling of a whole building, full new construction, or, you know, you're doing a full rehab of a project, then you can really start to get into modeling this. This tends to be a little bit of a discussion as you move further north in the climate zones. You know, zones 4, 5, maybe you're better off having a medium gray to give you some reflectivity and a little bit of energy gain in the wintertime. But we'll drill much deeper into that as we move on here. But yeah, good question about the prescriptive values. So here's one of the things that, you know, just sort of jumps off the table is it takes 4 times the cost per unit of energy to cool your building than it does to heat your building. That, of course, is the assumption based on electricity is being used for cooling and gas is used for heating. And again, we'll dive into that next, but you know, it really does make a lot of sense that this whole white roof reflectivity energy efficiency discussion really does fall into the idea that it's an air conditioning cooling cooling realm type of discussion. So the more AC you need over the course of a year, probably the higher reflectivity you're going to want to create a really energy efficient roof. So, but we can whittle this down to some extent on, you know, what are the heat sources from different parts of the globe or different parts of the country. So on the left-hand side, the circular graph is commercial space heating from Dodge or from DOE, sorry. And you can see it's the bulk is natural gas, but there's also a nice large chunk that's electricity, and then a little bit of fuel oil. So, you know, again, modeling for your specifics is really important. The right-hand side here is residential, and I've studied this chart so many times, and I think the way to break this down is anything that's in that red tone, we're using natural gas for heat. Anything that's in that blue tone, darker otherwise, darker light blue, is electric, whether that's a furnace or a heat pump, and then, you know, like the fuel oil for the other portion. So it's not clear cut that all buildings use electricity for AC and fuel oil, or, you know, natural gas for, you know, for heating. So, but there is that tendency, certainly in commercial structures, that we are using a lot more natural gas and fuel oil, certainly combined, than we are electricity. So, and we'll explain a little bit why that matters here as we move forward. You know, so, right, so we can use that 20% for commercial buildings nationwide, but again, you know, you can see Texas, Oklahoma, we've got some orange, we've got some green, we got some, I don't know, sort of darker orange, burnt red, I don't know. So it just depends, and different localities are going to have different preferences based on infrastructure. So, but what's important about electric heat, certainly from the commercial side, is that we need to always figure out and analyze, we need to include demand charges in our energy analysis. And so what is a demand charge? So this is an old time, I love this picture though, this is an old time meter on the side of your house. The top is your kilowatt hours used. That plate on the bottom arrow, that plate spins at different speeds. And so when it's nighttime and your windows are open and you've got one nightlight on, that lower plate is barely spinning. At 3 o'clock in the afternoon, every light in the house is on, you know, AC's running, TVs are all on. That's spinning significantly faster. All right, I know I'm combining concepts of commercial and residential, but the point is there. And so the faster that spins for this one particular period, that's our peak demand. So it's a time of use, extreme of use. And again, we'll show you what that means a little bit as we keep going here. So we do have demand charges all over the board, all over the board. So the darker color is higher demand charges. When down to the yellow means there's zero. The white, unfortunately, means we didn't have any data on this, or where we got the data didn't include that. We got this from the National Renewable Energy Lab. So there are a bunch of sections within Texas that don't have a lot of data on demand charges, which I would assume means there's probably not much demand charge, or we're using wind power or some other form and there just isn't necessary. But, you know, the darker shades, even that light orange has a demand charge of either $1 to $10, and then that next darker red or orange, you know, we're getting into $10 and $20 demand charges. So what do those numbers really mean? How does that $10 demand charge really affect our bill? And so if we look at a small office building, all right, we're looking at it one of the collar months here in April. You know, people are there from essentially 8 to 5, whatever. And so over the course of a month, we used 650 kilowatt hours. We didn't really have to run air conditioning much at all. Nice time out, you know, nice days outside in April. And so our total usage over the month based on kilowatt hours at 9 cents a kilowatt hour is, you know, right under 60 bucks, 58.50 there. If we have demand charges in place for our commercial structures, as far as I know, there are no demand charges for residential structures. It's only a commercial side thing, commercial side issue. If our AC came on for that one day and really drew a lot of energy, you know, our example is 7.2 kilowatts for that one period of time, that 15-minute period of time, then the billing even changes. It's not, so your demand charge is not based on kilowatt hours. Now it's based on kilowatts. So I pulled 7.2 kilowatts for that 15-minute peak period, made my dial spin as fast as it can, or it spun its fastest over the month for that period of time. And they charged 15 bucks for each one of those kilowatts. So your demand charge is $108 for those 15 minutes of use. Well, think about it. In April, if everybody's got their air conditioning off and everybody at the same time said, oh my gosh, all of a sudden today's 85 degrees, we're all flipping on our AC. So the utility has to provide that power. Maybe they have to start up their secondary plant to supply that proper amount of power. That costs them a hell of a lot of money. So we get these demand charges based on what utilities need to deal with. So we can think about this whole energy efficiency thing from a roofing perspective as how do we keep the demand charges very, very low? How do we bring this 7.2 down to 3 or 2? So we don't have this big demand charge. So if you're seeing information on energy modeling and we don't have demand charges included, you're not getting the right modeling. You're not doing the correct analysis. So we basically have shown that this is an HVAC discussion when it, you know, for the summer. That's where our highest demands are. That's where our energy use is highest. And I would presume that a electrically heated commercial building or resident, or maybe not residence, but an electrically heated commercial building could have a demand charge if you peaked your energy use in December and January. So again, something to look into what specifically the utilities are doing in that part of, you know, in that locale. So, and just to reinforce, you know, it really makes sense to do your own modeling. There's so many variations in what you can input, and you need it to match your project. So we as manufacturers and energy modelers can have all of these great models out there, but you know, if we say gas and electric and you are electric and electric, then that model doesn't work. So you got to pick the right model, or you got to input your own information. So here are 3 examples: Cool Roof Calc, Cool Roof Peak from Oak Ridge are a couple of good models to use. We at GAF have this, what we call CREST, this Cool Roof Energy Saving Tool. That is literally a faceplate, if you will, to get to the Oak Ridge National Labs. We developed that though as a really good submittal packet for roofing contractors to use when they're trying to show someone that a reflective roof can be a energy efficiency and a cost savings to a darker colored roof system, and justify the use of increased insulation as well. So, and then energy wise from NRCA is available, helps you figure out where your air barriers need to be and what levels of insulation you need and all that good stuff. So there's some things out there that are available. And if you get into some of these and you need to, you know, ask a question or something from us, just reach out, let us know. So we've taken all of this stuff into account, and we at GAF modeled 18 cities across the United States, is we really wanted to get into what we think was, at that time, the most detailed analysis for energy efficiency based on reflectivity of roof systems. So we used 2015 or 2016 energy costs. Again, we assumed gas heat, air conditioning, electric. We set our efficiencies at midpoint, and we used Cool Calc Peak to look at our models, or to do the modeling itself. So so what did we end up finding? So first of all, the difference between the blue and the orange here is we used reflectivity values for initial reflectivity and 3-year aged reflectivity. What we know in the roofing industry is that roofs will get dirty, that most owners are not cleaning their roofs annually. So white roofs get a little bit darker, lose some of their reflectivity. Quite honestly, EPDM gets a little bit of dusty, gets a little bit of dust and dirt on it, and actually the reflectivity goes up a little bit, which is just sort of unique from that perspective, but that is in fact what happens. So we use these 3-year reflectivity values to really hone in on what we think is the reflectivity of the roof over the life of that roof for the most part. So, and really what we're looking at here, without getting into the details, but I can certainly send you a paper if you need it, you know, estimated annual savings for a big box store with a highly reflective roof relative to a very dark absorptive, you know, non-reflective roof system. So these numbers can be quite large, and I know that's a big building, but if you're saving anywhere from $7,000 to $20,000 a year, there's a lot of savings in there over the life of that building. So a quick aside, we are trying to change the roofing installation discussion from what is the initial cost to what is the average annualized cost over the life of that roof. And I get, if I'm talking to University of Texas, they're going to have one perspective on their roof over 20 years versus, you know, developer style who is going to, you know, want to build a building and turn it over in short order. So, you know, we don't have our heads in the sand. We understand that there are different clients that are out there and different thought processes on what your roof should be. So, but what a lot of this entire study really showed is that, you know, cool roofs have those benefits in the north. And again, you know, electric heat, or sorry, gas heat, so it's inexpensive to heat in the north. Electric AC, so it's expensive to run your air conditioning when it's warm. And I think the further south we go, these ideas really become more understandable and very, you know, just you don't question them. We're running air conditioning 11 months out of the year, 9 months out of the year. Of course, a white roof reducing heat uptake into the building is going to do a great amount for energy efficiency. So, you know, we only covered gas heat and electric air conditioning. Other folks have done different things, and some of the studies that we've looked at really say that above what I sort of call, you know, the Mason-Dixon line, Atlanta to Nashville, sort of that line through there. There's folks pushing the idea that anything north of there should have a dark roof on it because you're going to get the benefit of the winter months in the solar gain. But that also gets often tied to the use of electric heat, which is much more expensive. And so it's using the dark roof with electric heat is actually changing the discussion from energy efficiency through air conditioning usage versus, you know, trying to save energy because our electricity is so expensive to heat the building. So they're trying to shift the discussion a little bit. And a lot of times these studies just don't have demand charges included at all. And you can see what the demand charges really do to the overall monthly bill. So we took the first study we did and took it to the next level, and we did gas and electric heat. We did assume air conditioning for everything. We, in addition to white, we used tan and gray membranes. We did set pretty high efficiency rates, thinking that this maybe was a bit more of a new construction type of discussion. And then we looked at 4 different levels for demand charges, anyway from 0 up to $25 per kilowatt, which, you know, unfortunately does happen. So, you know, again, from, you know, Texas, Oklahoma, we're probably in that 1 to 10, 10 to 12 maybe. So if for today we sort of focus in on that $5 number for a demand charge, I still think you might be surprised where we end up. You can see in the above United States map, the 13 cities we modeled for. The one in Texas is Fort Worth. So just a quick comment here. You know, we always talk about solar reflectivity. We don't necessarily always talk about emissivity, but of course, reflectivity is exactly what it sounds like. How much of the heat is reflected away? Emissivity is really about storing energy and then giving it back off. And one of my great examples is emissivity of your Craftsman crescent wrench, those silver ones. It's laying on your driveway in the sun, and you go to pick it up with your bare hand, and it is just smoking hot because it has absorbed tremendous amounts of energy and got really warm, and that all gets re-emitted back into the world. That if you put a piece of aluminum foil there, still quote unquote in that metallic form, but because of its design and its thinness, it almost retains no heat. So it has a very low emissivity. So just to try to put some perspective on that term emissivity, for most of us in the roofing industry, for most things in the roofing industry, emissivity is somewhere in the 80–90%, regardless of roof system type. So that kind of works out for us, which is one of the reasons why we don't talk about emissivity all that much. So in this study that we did with our 3 different colors, we looked at white with a 68 reflectance, tan with the 59, and gray with the 42. So Jason, to your question, yes, depending on the minimum requirements for cool roofing in a jurisdiction, the tan and the gray may not meet that. But if we are, again, doing some type of whole building energy modeling, then we may use these lower reflectance type of membranes for all of those other reasons we talked about, you know, reflectivity and visual aesthetics and all of that kind of stuff. So
it would really just be in reality, it's in climate zone 2 in Houston, that would just be aesthetics more than anything, right?
Sure. Yeah, absolutely. Yeah. Right.
Okay.
Right. So this is not a chart I'm going to explain. This is a chart to show you that we incorporated a lot of data, and we did a lot of number crunching to come up with all of the results on the next couple of slides here. So we look at, you know, all of these different climate zones or all of these different cities, and the 4 lines for each, the 4 horizontal lines for each one of the cities corresponds to the 4 levels of demand charges. If we want to focus in on the yellow $5, we go to Fort Worth, you know, where we have at least a $5 demand charge, we are showing upwards of 7,000 annual savings for, and honestly, I don't remember the size of the building that this was. I apologize for that. But our highly reflective membrane will provide significant savings. If we go to the same analysis, but with our darker gray TPO with a 0.42 Fort Worth, we're going to be down, with our $5 demand charge, we're going to save $4,000 a month. So still getting some good savings. But again, maybe aesthetically, this makes a lot more sense. Maybe people just don't want bright white. So absolutely. So what we've really shown is that reflective membranes still work. Winter heating penalty is not really a thing. Savings are of course reduced with less reflective membranes, but importantly, not eliminated, and that's really key. And then, I'm not going to go into this today, but we like thermoplastics at GAF with PVC and TPO, so we have our welded same. So all of this was in these two different publications. They're all double-blind, peer-reviewed. So real world data out there. If you're willing to look, if you're willing to read these papers, and reach out to me, and I can provide these for you if you really want them. So no problem at all. So you can go to gaf.com education and find them there if you'd like to dig around our website. I'm going to skip this Target study because basically what it says is Target, since they're in Minneapolis, all of their stores are white, highly reflective roofs, and they see no winter penalties regardless of where their big box stores are with their highly reflective roofs. So that's the Target story. With insulation, yes, the more insulation that we have, the less effective the roof color is, but it doesn't go away. So insulation always matters and is very important, but roof color is, really important as well. So in lieu of reflective roofs, we can use photovoltaics. These are actually parts of the building code that, if you don't have a cool roof, you can use solar, you can use vegetated roofs. So just to throw that out, that, these are options for building designers as we move forward with roof replacements and that. So final slide on this topic. Darker colored roofs generally mean higher energy costs across the board. Certainly big box, low rise buildings anywhere in the United States. So so that's really where we are with dark colored roofs. So 2 more topics, and I know we're at a quarter till, but that's okay. I can get through this. Don't worry. So let's talk about thermal bridging. So what we know is we do have a bunch of insulation prescriptively required. So we can see that 2015, 2018, 2021, the insulation values have stayed the same. They didn't really change all that much from 2012. But, just a quick point, how we install this insulation really matters. So take a look at this roof. So this is snow. I took this picture when I was in Nashville a couple of years ago, looking down from an elevator lobby, and every single one of those little black dots on that white roof is where the fastener and plate that is directly underneath the membrane is transferring the heat from the interior of the building through that fastener up into that plate and then melting the snow. So this is a classic example of thermal transfer through fasteners that happens 24 hours a day, 7 days a week, 365 days a year. So how we install our fasteners matters. So this is a classic, we use this all the time. We put fasteners through our seams in our mechanically attached systems, or we attach all of our thickness of insulation and then we adhere a membrane on top of it. If we do some quick calculating and we look at field perimeter and corners with this many fasteners per board, which I know is a bunch, but there are some high wind zones in Texas and along the Gulf Coast where you will need very large quantities of fasteners in the boards. So we're really getting into either one fastener per square foot or one fastener for every 2 square feet. So since these are all thermal bridges, what is that doing to our insulating value? You know, we all wanted to put in R25, so we put in 5 inches of polyiso, and then we run one of these metal fasteners with a large plate on top of it, you know, 1 every square foot, 1 every 2 square foot. Another good example of how this thermal transfer is melting the snow and you know, bringing the heat out of the building. So just again, another example from the exterior on it without the FLIR camera, you wouldn't see any of this, but with the FLIR camera, you can see all the differences in temperature there. So in the roofing industry, a group got together, a bunch of consultants, Simpson, Gumpertz, and Hager, University of Florida did some work. And really what we learned with all of that is with 1 fastener for every square foot, so a 4x8 polyiso board would have 32 fasteners in it, we are losing, let's just call it 30% of our R value. That's a lot of loss. So that R30 would really be an R21 if we take into account the thermal loss of those fasteners. Probably a little bit more realistic from a wind uplift perspective is if we have 1 fastener for 2 square feet, which is the red X on the chart, where then our overall R value loss is somewhere in the 16-17%. But even so, on a 30 or an R25, we're still losing 5 or so R's. So we're not getting what we paid for by simply adding all of those fasteners in, which are really important for wind uplift. So we've got to make a trade-off. So we did more studies and we looked at 6 roofs. We looked at overall R value. We're going to go through just 3 of these real quick here. So case 1 is sort of the worst case scenario, if you will, from a thermal bridging perspective. Fasteners all the way through the thickness of the insulation directly underneath the membrane. And then, so those are traditional fasteners. And then we looked at induction welded system in case 2, which you probably know better as the Rhino-Bond system from OMG. And that just has a different ratio of fasteners because of its the way that roof system is installed. And then our case 3 here, where we had fasteners through the lowest level of insulation, and then we actually adhere the top layer of insulation and the membrane, effectively burying the fasteners. You can see where this is going already, can't you? So we looked at all of the costs associated with fastener bridging. We looked at the blue line is really loss of insulation that was paid for, but we didn't achieve because the R value actual was less than R value design. So then we looked at fastener costs, adhesive costs. We only have adhesives in case 3 because that's where we used our adhesively attached membrane and ISO board. And then we look at how much energy we are going to use over the life of that roof. And what this chart is hoping to explain is that case 1, our traditionally attached, mechanically attached sheet with a couple layers of ISO, because of the large energy use, is not really that much more expensive than if we built this really expensive roof, and I say that sort of facetiously in air quotes, that we mechanically attach the first system or the first layer, then we adhere the ISO and the membrane. That brings in this big cost of adhesives. It makes our ISO boards extremely efficient, and we use significantly less energy annualized over that roof because of its improved R value. If we double the life of this and go from 15 to 30 years, we actually now are seeing that our adhered system with high R value, highly efficient R value layer is actually ends up being cheaper the way we modeled this. So I think, you know, practically we can understand this concept that if we don't have all of that insulation penetrated by fasteners, we're going to end up with a more effective insulation layer. So if we keep moving on, what does this sort of look like in reality here? So if we fasten that first layer of insulation, adhere the next layer, you know, use foam to adhere a fleece back membrane, you know, we can design these very practical systems that, you know, might be a bit more to install up front, but over a 15 or a 30-year life are actually going to save the building owner money and do great things for energy efficiency overall. So sometimes it's not just about the money, it's about what good we're doing for the environment. So lost R value through thermal bridging means a lot higher energy costs over the life of the roof system. So that's where we are with that one. So let's talk about airflow. This is one that I don't think a lot of people really spend a lot of time talking about, even though we do have air barrier requirements in the Energy Conservation Code. So just reiterating what our R value chart is, and what we're showing in the bottom chart here is really what we call the law of diminishing returns. If we add 1 inch of ISO, and then we add another inch of ISO and another inch of ISO, and we keep doing that, our cost is the same per unit, but our effectiveness of actually increasing, you know, the energy efficiency starts to go down. So we're seeing that actually with our code bodies not really increasing our R value that much, or required R value, over the last 5-7 years. So that's why in 2012, the Energy Conservation Code went to the concept that all buildings need to have air barriers. And so we know insulation and air barriers do a really nice job of energy efficiency for buildings. So we have different kinds of air movement actually in and throughout our structure. So we have flat out air infiltration, that we can call that an air leak, if you will. We have air exfiltration, that's also an air leak. So then what we also have, which we don't often talk about, and I don't think the industry is really talking about, is air intrusion. So that's interior air getting up into the roof system, bringing heat and moisture, you know, on a cold winter's night, on a cold, even a cold fall night, that membrane can get colder than the ambient temperature. It can reach the dew point, depending on the interior humidity levels, and we can get condensation underneath the membrane. However, that membrane meets the building code requirements, the minimum building code requirements for being an air barrier. So what if we put that air barrier at the deck level? So, you know, just because the membrane can be an air barrier doesn't mean it should be considered an air barrier, or, you know, and not put something at the deck level. So why does this all matter? You know, International Energy Agency says, you know, realistically, I'm reading from the middle paragraph, 20-30% savings in energy efficiency in cold, probably 5 to 10% energy efficiency, certainly in warmer climates. The nice thing about Texas, and where we have lots of heating degree days, the air drive is generally from the outside to the inside, but not always. So these ideas do play specifically within all geographic locations. So if we look at air barriers in the codes, you know, 2012 IECC, new construction, provide an air barrier around the entire envelope. So, you know, unfortunately, from a existing building perspective, when we do a roof recover or roof replacement, that doesn't come into play. and I'll just throw out this, if we have a low building, large, big box, and we can figure out how to air seal the roof a little bit better than it had been, are we not reducing our leakage and doing some preventive measures for energy efficiency versus just not really worrying about whether or not we've designed an air barrier and a roof recover, roof replacement, to be most effective. So something to consider as building code officials that are out there. So we know that there's 3 ways to check the air tightness of a building. We can do this whole building blower door test. I'm sure you guys are familiar with a lot of this. We can do testing of specific materials, and then we can do assembly testing. And a good example of that would be a window within a wall section to see how well that window tied to the wall prevents air leakage through the interface there. Within IECC, there is a decent list of what we call deemed to comply materials, so that they are air barriers. So you can see top bullet point, fully adhered roof systems, single plies, BURs, modified bitumen, and a whole laundry list of just other individual types of materials that are used in the roofing industry and the building exterior industry. But for us, looking at BUR, mod bit, adhered single plies, most of them are deemed to comply. What's important is that even a mechanically attached single ply can be considered an air barrier. The manufacturer has to test it, has to provide an evaluation report because it's not in the specific list in the building code, but we can use a mechanically attached single ply membrane as the air barrier, and we comply with the building code. So what might that be? Why might that be problematic? So we know that air barriers to really function really need to limit, or they need to be continuous around the building so that we don't have those air intrusion or extrusion locations, and certainly where a roof meets a wall, we run into that quite often. But what I just brought up earlier was if we have this infiltration into the roof, what kind of bad things could really happen at that point? And I know I'm running up on time, but I got just a couple more slides for everybody here. So let's walk through what would be essentially 4 basic roof designs that all meet building code. Single layer of insulation, mechanically attached. A lot of conditioned air readily gets in. I will say that as of the 2018 IECC, this system is no longer allowed because the code requires 2 layers of insulation, which is a good segue to this. So mechanically attached membrane, 2 layers of insulation, board joints offset and staggered. Our friends up in Canada showed us that just from the top to the bottom configuration here, we reduce air infiltration into the roof to the underside of the membrane by some 60%, just by having 2 layers of insulation with board joints offset and staggered. So that's why that's an important component in the IECC. If we go to our next level, if you will, and we adhere our upper layer of ISO and our membrane, now we don't get that billowing. So we don't get the billowing when the wind blows to actually draw air up into the roof. We also need to recognize that buildings are internally pressurized. So turning on your air conditioning or heating pressurizes the building and pushes more moist air, conditioned air up into the roof system, into the walls of the building. So where we put our air barriers really matters from a thermal efficiency perspective. And then if we go a step further, we could put an air barrier over a rigid board. Maybe we adhere everything above that if we don't want to poke holes in our air barrier, or we can secure that with some fasteners through the first layer of insulation. So again, all of these meet building code. All of these are good solid roofs. We'll keep the water out, we'll stay on, we'll have longevity. but from an energy efficiency perspective, you know, number one, there's our basic. We're getting a little bit better on the bottom, and then we're getting better, and then we're getting better. So things to think about as we design, and again, taking into account, you know, initial cost versus overall annual cost is important to think about here. So buildings with air leakage really mean higher energy costs. So let's just wrap up real quick. This will just take 20 seconds. So cool roofs are reflective. I think everybody in Oklahoma and Texas recognizes that just by daily experiencing life daily. Reflectivity is good when it's really hot out. Thermal bridges of fasteners is really an important concept that most of us just aren't really talking about. And then air barriers at the roof deck is another idea to improve our energy efficiency. So if we're going to package this all up, an adhered roof membrane over an adhered HD or polyiso board with a couple of layers of insulation, fastened only at the bottom, with an air barrier perhaps at the base, is one heck of a highly energy efficient roof system. So Jason, I'm sorry I ran long.
Oh, no worries, no worries. We're
But I
a couple
think we're
minutes
good to
over.
go. So
I'll keep my questions to myself, and we'll answer the audience's questions. Tell you, my mind's a little bit blown about. Never even thought about demand charges on the energy modeling.
right.
That's, and then third. So in a high wind area, did I hear you right? Well, you could reduce your effective R value by 30% with fasteners.
Yeah, and
That's
quite
amazing.
honestly, even in a non-high wind zone where we just install a single-ply roof system with traditional mechanical attachment in the seams of the membrane, you know, a 10-foot on center or a 10-foot wide sheet, seams or fasteners in each one of those, you know, with a few insulation fasteners just to keep the insulation in place, we could easily end up with one fastener per 2 square feet over that entire roof.
Yeah.
You know, so 100,000 square foot roof could have 50,000 fasteners in it. That's 50,000 thermal bridges.
Yeah.
And at one fastener per 2 square feet, we're losing 15 to 17% of our R value. So that's a big deal.
Wow. Wow. And Robert asked a question, and it was back to that cool graphic about the reflectivity. Where does the reflected energy go? It has to go somewhere, doesn't it?
You know, it does have to go somewhere. Sometimes it hits the clouds and sticks around. Sometimes as our weather folks on TV will tell us, you know, it just reflects back up to the sky. And if we have cloudless skies, the heat energy just goes up into the atmosphere and leaves the globe, if you will, leaves the atmosphere. That is an architect trying to tell you how that actually works. And so don't run with that too far, but that's essentially accurate. It just goes up into the atmosphere and goes away. Okay.
And Benjamin's has been answered already as far as the thermal bridging. You covered that. He must have asked that before you got to those slides. Well, that's it. I'll keep my other ones for. That was a great job, James. If you've got any more, I'd love to have you back in a few months. If you got another presentation, that was really good. I really appreciate your time. Got a couple more comments.
We can talk about that. We have lots to talk about. So GAF, happy to help out.
Awesome. Well, fantastic. Well, thanks for joining us, everyone. Go ahead. What time is it? It is 2:05. Why don't you go ahead and take the rest of the day off? Tell your boss I said it was okay.
Love it.
Awesome.
All right.
Thanks, everybody. Thanks again, James.
Thanks for the nice comments in the chat, everyone. Much appreciated.
Fantastic. Bye, everybody.
All right. Thanks.